Hi, folks. So today, what I'm going to do is I'm going to be going over bonding. Okay. And in particular, we're going to be focusing our attention on ionic bonding. So, one of the reasons for things to bond is because they're trying to reduce their potential energy. And so, a good understanding of this is to make sure we understand what a chemical bond is. So, it's a mutual attraction, electrical attraction between the nuclei. And I want to remember that the nuclei here are positive, and the valence electrons and the electrons here are negative. Okay. And so, because of that attraction, they want to stick together, per se. So the reason why bonding occurs is to reduce their potential energy. This is why we don't find elements by themselves in nature. What ends up happening is that they're too much potential energy, and so they become extremely unstable and reactive. The only substances that are less stable, or sorry, more stable, I should say, would be the noble gases. Okay, noble gases are stable by themselves because their shells are full. Okay, so here I have a diagram here of potential energy. Okay, so we're going to reset this. I'm going to set this to be oxygen. And what I want us to look at is to focus in on, and in particular, I want us to focus in on the idea of, okay, the energy here. So if we look right down here, you can see that there's a little ball, and this is representing where the energies are. Okay, you can see the potential energy is very, very low. And because the energy is very, very low, um, that means that it's reached its best stability, the lowest potential energy. Now, what I'd like you to notice is I'm going to pull this oxygen away, and I want you to notice what happens to the potential energy. We can see the potential energy start to increase. The reason it's increasing is because of the fact that now we don't have that attraction between the nuclei and the electrons in the other atom. Okay, so when we bring them back together, we end up reducing the potential energy because we are sharing the electrons or stealing those electrons there. Now, if I get the nuclei too close, because they're both positive, what ends up happening is the potential energy becomes great. Okay, so again, I'm going to drop it back to its perfect spot right down here at the bottom. But then notice when I push the nuclei closer, the energy goes way up. Okay, and so now what I'm going to do is I'm going to let go, okay, because I'm basically forcing them to stay together, and I'm going to let and see what happens. And we can see that the atom itself pushes away because of the repulsion of the nucleus. So there's a perfect balance between them both, okay, that we need to make sure that we get. So there's two main types of bonding. We have ionic bonding and covalent bonding. And ionic bonding results from the attraction between cations and anions. Cations are positive ions, anions are negative ions. It's caused by the transfer of electrons. While covalent bonding results from the sharing of electrons between two pairs or between pairs of two atoms. Okay. So how do we know the difference between the two? And the way we know the difference between the two is by looking at their differences in electronegativity. So I want to make sure that we remember, what does electronegativity measure? So electronegativity measures the ability of an atom to attract electrons. And so the smaller the atom, the greater the electronegativity. So the right-hand side of the periodic table has the greatest electronegativity, while the left-hand side of the periodic table has the lowest electronegativity. So to determine which type of bonding we have, we compare the difference between the electronegativities, okay? So in ionic, we have a big difference of 3.3 to 2.1 in electronegativity, but in covalent, it's about 2.0 or 2.1 to 0.0, okay? Now, we won't be using this much because what we're going to be doing is looking at as to where their location is on the periodic table. Okay, so let's talk about ionic bonding. Okay, so ionic bonding forms when a positive ion and a negative ion are attracted to each other, and this is a result of an ionic bond. The force that holds it together is because of the electrical attraction, the positive and the negative. And an ionic compound, by definition, is composed of positive and negative ions, and this is probably the most important thing. It's composed of positive and negative ions that are combined so that the number of positive and negative charges are equal. Okay, so let's take a look at this. Now, what I'm going to assume right now is that you can draw or model of an atom given a periodic table. Okay, so we should be able to do this. So let's take a look. Okay, so an ionic bond. Here we have two elements. Okay, so the first one, the way we can tell what element it is we can look at the number of protons here. So if I look on a periodic table, I will find that this is sodium. Okay, And then on the right-hand side, because it has 17 protons, I know that this is the element of fluorine. Okay, now, which of these two has the greater electronegativity? Well, the winner is going to be chlorine. Chlorine has a higher electronegativity. It's on the far right-hand side of the periodic table, so therefore it has a higher electronegativity. Sodium, on the other hand, is all the way over on the left-hand side of the periodic table. So it's bigger and it's going to have a lower electronegativity. So what chlorine is going to do is it's going to literally steal an electron from sodium. When it steals an electron from sodium, what we end up with is a total of 10 electrons now. And because we now have 10 electrons and 11 protons, we now have a +1 charge. Okay. On the other hand here, now over on the chlorine side, we have 18 electrons. And when we have that 18 electrons and 17 protons, we now have an extra -1 for the electron amount. So we can see that the charges here, we have a +1 and a -1. And I know that this is correct because of the fact that when I have a +1 and a -1, they cancel out. So we end up with a net charge of 0. Now, here's the interesting thing. If we look and we count, we're going to see that we have now 2, 4, 6, and 8 valence electrons. So this looks like neon as a noble gas. So on the outside, it looks like neon, but on the inside, it's still sodium. On the other hand, over here on this side, we're going to have 2 because we added an electron over there, stealing from sodium. So we have a total of 8. So again, this is going to look like, so this looks like argon. Now, it's not argon. And the reason it's not argon is because it still has 17 protons. So what we've made here is sodium chloride. So the idea is there's a transfer of electrons that takes place. The one with the greater electronegativity steals the electrons from the element with the lower electronegativity. So let's try another one here. Okay. So in this one, we have an example. The element here on the left-hand side is magnesium. The element on the right-hand side here is oxygen. So what ends up happening here is, again, we want to get it to where it looks like a noble gas. So if we look at the oxygen has got smaller, it's going to have a greater electronegativity. It's found on the right-hand side of the periodic table. Magnesium, on the other hand, is larger, and it's going to want to lose that outer electron, again, to have the electron configuration of a noble gas. So what ends up happening is the oxygen will steal one electron here and steal another electron here. When it does that, this now has a total of 10 electrons. And because it has 10 electrons, the net charge becomes -2. On the other hand, the magnesium here becomes a +2 because it has a total of 10 electrons. Why +2? Because the proton number is 12, and we have a total of 2 electrons that we've lost. Okay, so we end up with magnesium being a +2 and oxygen being a -2. So again, the charges are equal and opposite. Okay, now the oxygen here, it looks like neon. It's not neon. Okay, and the magnesium here looks like neon. Okay, so both of them look like neon, but they're not because the proton number remains the same. And so we still end up with a compound, and here we have magnesium and oxygen, okay, that we have made. Now, we could do this all day, but the thing is I want to make sure we understand that it's a transfer of electrons that takes place, and the reason that they're doing this is to lower their potential energy, and it also makes it so they become very stable electronically. And the most stable elements on the periodic table are, for example, the noble gases. You got helium, you got neon, you got argon, you got krypton. All of those are the most stable elements on the periodic table. So ionic bonding typically creates 8 valence electrons. 8. Okay, that's the magic number on the outer ring, similar to the noble gases. And this is often referred to as the octet rule. Octet means 8. And you can see here it's a repeating pattern. So this is actually a picture of sodium chloride. Sodium chloride here is a crystalline structure. It's a repeating pattern of positive, negative, positive, negative. And so you can see that it forms perfect little cubes. Now, we do need to know this thing about valence electrons. Valence electrons are the electrons in the outermost ring, okay, the outermost ring. So what we do is we don't need to worry about the inner electrons, we'll worry about the outside electrons. And the coolest way to remember the number of valence electrons is it correlates with the group number. And so if you look at the periodic table, you can see here I have a list of the valence electrons for this is period 2 on your periodic table, period 2. Okay, so lithium has 1 valence electron because it's in group 1a. Beryllium has 2 valence electrons because it's in 2a. Boron is in group 3a, and so on and so forth. So we can actually use the periodic table as a giant cheat sheet. So if we look at our giant cheat sheet, if I wanted to know the valence electrons for calcium, I would look up here at the Roman numeral and I would see that's 2, so it has 2 valence electrons. If I wanted to know for selenium, element number 34, again, I look at the group number up here and I can see that it's 6. And so that will tell us what the number of valence electrons are. Now, if we haven't figured it out yet, the inner electrons don't play a role here. It's the outer electrons. So a gentleman by the name of Lewis came up with a way to simplify the way in which we show the transfer of electrons. And what he did is he came up with what is called the Lewis dot diagrams or electron dot diagrams. Okay, and so what he did is instead of thinking of looking at the inner electrons like in Bohr's model, he just looked at the outer. So if we use a periodic table here, we can determine the number of valence electrons in beryllium. Okay, so I'm going to take a step back. So if we look at beryllium on the periodic table, I can see it's right here. It's in group 2a. So that has a total of 2 valence electrons. So the way I would show it would be a dot and a dot. 2 valence electrons. Notice I didn't pair them together at all. All right. For the next one, we have carbon. So again, if we go back to our periodic table and find carbon on the periodic table, we can say that it has 4. Okay, so moving back, all right, or I should say moving forward, we're going to put 1, 2, 3, and 4. 1 on each side before we start pairing up. So think of it as like a box, and we put 1 on each side before we start pairing up. So notice how I remove the box. So we really don't draw it with the box. And what I'd like for us to do is then look for oxygen. So if we find oxygen on the periodic table, I find it right here up at the top. Okay, and it's in group 6a. So again, we put 1, 2, 3, 4, 5, and 6. Notice I started pairing up after I got past 4. Okay, and this is going to help us with bonding overall. So we can show the bonding using this method instead. Okay, so what we're going to do is I'm going to show you how to do this instead of drawing the Bohr models, which are a lot more complicated and require showing the inner electrons. So here we're going to show it without using the inner electrons. So my first example here is calcium and chlorine. Okay, so first thing, you got to get a periodic table and find calcium on the periodic table. So if I look for calcium on the periodic table, calcium is in group 2, and so I know that it has 2 valence electrons, so 1 and 2. Chlorine, on the other hand, is in group number 7a, so it's going to have a total of 1, 2, 3, 4, 5, 6, and 7. So here it is. Chlorine has the greatest electronegativity, while calcium has the lower electronegativity. So again, remember, electronegativity measures the ability to attract electrons. So chlorine's the one that's going to steal electrons. How many electrons will chlorine like to steal? Well, chlorine would ultimately like to steal a total of 1 electron. When it steals that 1 electron, this chlorine becomes -1. Okay, this chlorine now has 8 valence electrons, 8 electrons in the outermost ring. It is satisfying that octet that it's trying to achieve. But here's the problem. This calcium is not. It still would like to lose 1 more electron. So what that means is we need to bring in another chlorine in order to steal an electron from the calcium. So we take another electron from the calcium. The chlorine becomes -1. The calcium becomes a +2. Now, what is -1 plus -1? That's -2. And we here have a +2. So what we know is we've made the correct substance, and calcium now has an octet, and the chlorines both have an octet. Now, in order to label over here the cation always the positive ion. So we would label this as Ca+2, okay, because it's the positive ion. The chlorine now has become negative. So the anion here is Cl-1. Now the formula is when we put them together. So how many calciums do we have here? You're right, just one. How many chlorines do we have here? We have two. So if we write the formula here, the formula for this would be Ca, because we only have one calcium, Cl, and we put a little 2 to let us know that we have two of the chlorine. See, I've got one here, and I have another here. Okay? So the idea is that charges need to be equal and opposite. We need to transfer electrons until we get to each one of them having an octet. So let's try another one. Okay, let's try it with aluminum and chlorine. So if we look here, all right, I've got aluminum, find it on the periodic table. Okay, when you find it on the periodic table, you should notice that it's in group 3A, so it has 1, 2, and 3. Chlorine we've already done, right? That's in group 7A. So there's 1, 2, 3, 4, 5, 6, and 7. Okay, so again, the chlorine's going to be the one that's more electronegative. It's smaller. The aluminum, on the other hand, is bigger, so it has a lower electronegativity. So the chlorine's going to be the one stealing the electrons. How many electrons is chlorine going to want to steal? Well, it already has 7 valence electrons, so it only needs to steal one more. So it steals one from the aluminum here, becoming a -1. The chlorine is happy as can be. It follows the octet. It's got 8 valence electrons, but the aluminum would still like to lose 2 more electrons. So that means we need to bring in another chlorine. Okay, so we bring in another chlorine, which has got 7 valence electrons, and it steals. So this now becomes a -1. The chlorine here, satisfying the octet rule, but that aluminum still would like to lose one more electron to get to an octet. So we need one more chlorine to come in and steal an electron. Oops, I drew one too many electrons. Let's erase that. There we go. Okay. And so therefore, it will steal the electron here. And this becomes -1. Now, because the aluminum has lost 3 electrons, it now becomes +3. Okay, so overall, over here, we have -1, -1, and -1, which is all -3. And a +3 and a -3, when I add them together, +3 plus a -3, that equal 0. Okay, all right, so for the cation here, the cation is the positive ion, so we would list that as Al+3. The anion here is Cl. This is the negative ion, -1. Now, this is where it gets interesting. We write the formula. How many aluminums do we have here? Well, if I look, I only have one. Okay, how many of the chlorines do I have here? Well, if I look, I have 1, 2, and 3. Okay, so I would write Cl3. That would be my formula. So what I want you to do is I want you to try this here in class right now and see how it goes and walk yourself through the review worksheet. Have a good rest of your day.